So the ECMWF has quite an interesting makeup of our HPC workloads in that we do quite a lot of different things, that may be weather forecasting, climate work, reanalysis, and there's lots of research. But particularly we have a divide between a time-critical workload and a non-time critical workload that have quite different characteristics. The bulk of the workload is made up of research workload, but most of our systems are actually optimized for the operational workload, which sort of justify our existence. And this leads to, we kind of have two main goals. We're both trying to minimize time to solution and maximize throughput, as everybody is, but we're also very strongly interested in reliability from the perspective of minimizing the worst case runtime. What happens when everything goes wrong, when jobs fail, nodes fall off, and file systems degrade or similar. Now, I'm not a meteorologist, so I'm not going to talk about any meteorology, but I have a particular perspective on the workflow that we've got, and as far as I'm concerned, everything begins when the model starts producing data. So we get data in the form of fields. These are two-dimensional slices of the atmosphere that surround the atmosphere, essentially like shells of an onion, skins of an onion. And we've got quite a lot of these. We have, at the moment, about 18 million fields produced over an hour. And this comes to about 20 odd terabytes, depending on how you count it. And this is stored in Lustre. It gets stored onto the file system into a bit of technology that we call the fields database, the FDB, which isn't really a database, but that's historical naming for you. So this data is then loaded, read again from Lustre by our post-processing pipeline, which does regridding, resampling, and produces a range of products for our customers and clients in the member states, which was also written back out to Lustre and read back in from Lustre to the dissemination systems before it's sent off over the wire. And this all happens within a time-critical path, which is we have an hour from when the data assimilation is finished to produce the forecasts. We also have processes that happen outside the time-critical pathway, in particular the archiving, which we're talking of the order of 100, 110 terabytes of data going to archive every day. Our big problem is we've got a scalability problem. Every time they bump the resolution, we get a factor of 4 in the amount of data that we're talking about, and we also increase the number of vertical levels in the atmosphere and the diversity of the data that we're looking at. And this is slightly older data. It's from a couple of years ago on the left. It's increased a bit since then, but this is the daily data produced from 2 time-critical runs. And as you see, we're going to have a very, very substantial increase in both the amount of data and the number of bits of data. And a huge increase in the volume that's sent to archive, because a lot of stuff is sent to archive from research. So I'm now going to look at the component in the middle of that pipeline, which everything goes through. Sitting on Lustre, we have the fields database, version 4. It's an in-disk index of meteorological fields. We store this on Lustre with an in-disk index, fundamentally so we don't have to rely on external processes outside the supercomputer that add additional operational complexity to keep them up and running. So we don't have extra databases running, we don't have cloud services doing all that sort of stuff. This is on Lustre. And this software is actually a library. We link it into all the processes that are running. It's not a service. So when we write data out, according to various rules, we select an output directory for the run, and each process starts writing data into a data file. And these are independent messages, and they come out in the order that's dictated by the scientists. Then an entry is appended into an index, which allows other processes to come in and find the data correctly. And this index is very simple. It's a flat list. It's kept in a file. The complication comes that for having multiple outputting processes, we're currently using MPI to synchronize access to this file. And it actually works extremely well. It's quite performant, and the whole system works. So, and this takes long until we've got a full data set. So what are the issues with this? Why do we want to replace this system? Firstly, we have to manage the consistency very, very explicitly. Because we use MPI to control access, we can only have one component of the workflow accessing a database at any point in time, only one at a time. And we have to manage our workflow to make sure that we only have one writing component to any of the subcomponents. This means our data collocation, the schema where we put the data, is ultimately determined by technical details of how we've subdivided the workload. This is not particularly nice, and it makes things difficult to change in the future as well. It's not transactional. If things fail, we can end up with part written data, written index records. Really quite horrible stuff can happen. And essentially, when we rerun components of the workload, we have to just wipe the data that's in this intermediate store and start again, because otherwise we don't know what we're going to end up with. And it's very difficult to work out what's gone wrong. If something has gone wrong in our consistency management and two processes have tried to write to the same place at once, who knows what will happen? We'll have corrupted index files, data files with part-written data. Someone might have gone back and tried to rewrite data that is already there, but because it's compressed, you'll end up with a different size, and you end up overwriting data, and just things generally can go wrong. And the overall takeaway from that is that trading consistency for performance incurs a cost on the people who are running the system, rather than a technical cost, and this is not ideal. So, one of the major approaches taken in cloud computing and other types of data services, and particularly in the realm of big data analytics, is to use object stores, where you pass a piece of data with some associated metadata off to a service somewhere, and this data gets put somewhere, you don't really care where, and you get back some form of handle by which you can access it later. And we're in quite a nice place that we've been using object storage for 30 years. MARS, the Meteorological Archiving and Retrieval Service, is an object store. We don't care about files. That's not the realm of MARS. We access data through the MARS language, which is a semantic description of what data you've got, formed of key value pairs that actually have meteorological meaning. You can work out in advance what those keys are going to be. You don't have to communicate OIDs around, and this gives a very structured and systematic way of accessing data, which can involve things like range parameters. You can have wildcards, and you can search things semantically based on what you're looking for. And you can see here we've got an operational and a research data collection. And it's a unique way to describe any of the data we've got, and it's a semantic way to describe the data that we've got, and it's quite nice. This does come with a cost. The cost is one of data governance. We have to maintain a consistent access pattern to all the data that we've got, but the whole historical range of data. And we have to make sure that the metadata keys aren't going to collide with anything current or in the future. But we've been doing this for, as I said, 30 years, and actually having that archive of curated data accessible in a systematic way is a really good thing. So, how does this link to the FDB? The FDB is essentially a cache sitting in front of this object store. The MARS archive has disk-based caches and tape libraries, and provides a consistent interface for users to access any data in the perpetual archive. But it's not really designed to feed large amounts of data to compute nodes in parallel. It's not really its job. So the FDB sits inside the high-performance environment and works very nicely. And what we'd like to do is to properly integrate the FDB as part of the MARS ecosystem. We want to be able to use the same software, but the same semantics to be able to access the data. Currently, the two bits of software have different pedigrees, and the keys that you use to access the data are not quite the same. And we want to be able to build it's essentially a hierarchical storage manager with more layers that's application controlled, which allows us to move data up and down the stack preemptively for when it's needed. One of the big advantages of doing this will be able to make use of the facilities within MARS to directly move data between the FDB and the rest of the Mars infrastructure without involving other nodes in the process, because currently we're having to read data out and write it back into Mars, which takes up network and compute resources that could otherwise be used for other things. So we have a new design for our FDB, which tries to eliminate some of the problems that we've got. And we start with a process that wants to write meteorological data in grid format into the FDB. And the library selects a path for the database to be put in that's based on a runtime controllable schema, which is stored inside the database so that we can then change the schema but still be able to access existing data. And the first thing that happens is we create a table of contents, a single table of contents. The process then writes data to a data file in the normal way and starts building an index, a B-tree index in memory, which contains references to that data. And it continues until it has written all of the data that it wants. And the very, very last thing that it does, it writes the index to disk, and when that's done, it appends an entry into the table of contents that makes that data visible to the outside. And that's a single transactional step that makes that visible. Another process then comes along, and it writes data to a data file and builds its own independent index. And hopefully we have quite a lot of data per index, and then it also appends to the table of contents. And what we've done is we've pushed this synchronization problem from using MPI to being one that depends on the POSIX semantics of the file system to make the append operation work correctly, because you can open a file in append mode and write in a uniform manner. This means that we can have completely unrelated processes writing data into this system which don't have to know about each other, which means that we can, for instance, run processes at the same time, and we don't have to structure the data entirely according to very hard delineations of how we've laid out our process in time. I've highlighted here that these two elements in the index have got the same key. If you write things in with the same key, we can set this up such that the newer data masks out the older data, but all the data is still there. You can see exactly how you've got in the current state. You can have a process that's produced invalid data, and you can go back and correct that data by putting new data in. And you can very, very easily trace how you've ended up in the situation that you've got. You also have the advantage that if a process is running along, writing data, and something goes very badly wrong, it has never added an entry into the TOC. So we don't care if this index is written to disk or not. We don't care if it's corrupted. We don't care what's happened to the data. If the data is not valid, the data is not visible, which is very, very good from a robustness perspective. However, there's a slight snag in all this. When we're writing to a parallel file system, we're now dependent on the append operation to the table of contents. And empirically, we can do 11 appends per second. This seems to be, on the file systems that we've got, seems to be a relatively asymptotic limit when nodes are competing to do that. And once you cross that threshold, nodes will just be queuing up, and you introduce essentially arbitrary delays into your write process. When we're considering an ensemble forecast, we have 52 forecasts running in parallel, at least 10 writers per ensemble member, and 240 steps. The 240 forecast steps are important because data is not visible to the outside until we've appended to the table of contents. So if we want to incrementally make data available, we need to write incremental indexes and append these onto the table of contents. So an absolute minimum that we would need to be able to support this mechanism would be 35 appends per second. And there's a bit of a problem here. So the first thing we can do is go part way back towards what we had with the old FDB, that we segregate the data into logically independent units. We pick the logical unit that you might rerun, i.e. the operator sitting in the control room sees something's gone wrong, they kill that bit and run it again. And that essentially defines a data stream that's quite useful to be able to wipe that data stream or continue that data stream or restart it in one sense. And we do this with a schema. So we have a 3-level schema. The first level essentially determines the directory that we write to, and hence the table of contents that's used, and that determines the number of appends that we have to do. The second determines how we collocate data within data files, which is relevant for performance in the post-processing stack. And the third determines the keywords that can vary within a data file. And you can see we have a schema that we can define. The data governance team can define these schemas for all of the different types of workload that we have. But this is still not enough. We don't get enough performance out of this for our big ensemble forecasts. So what we do is we cheat. The first thing that happens when we are running in parallel in a large MPI job is we do something a bit different. We add a subtoc entry, and each process gets its own table of contents. There's now no contention on these, and we only have to do 50 appends to the overall table of contents in an hour. We can do these we can start these appends right at the start, so we're not even waiting on them in the data pathway. They just get done, and it's no longer a performance bottleneck at all. Each process then writes its own data files, creates its own indexes, and appends to its own table of contents independently. This data becomes visible to everybody. And for each step that we want to become visible to the outside world, we add another index to the local table of contents for that process. This does make the read pathway a bit more dependent on file system caching, and you have to follow a chain of entries and indexes to be able to find your data. This works. It's not optimal from a read perspective for later. So the last thing that we do when a job successfully completes is we take all of the data that's been written in all of the indexes for one process and write a super index, and finally append this onto the master toc, masking out the original subtoc. So we now have a scheme where we have quite efficient data access, and we haven't had an append bottleneck through the write process. So now we look at the read performance, because the write performance is now good. We're ultimately dependent on the bulk data transfer rate to the parallel file system. That's what parallel file systems are for. And we find that we're actually quite similar to the old fields database. This is probably not surprising. We're limited by the bulk rate of reading data off disk when things work well. These numbers here are some new read performance numbers. They are a bit different to the ones in the paper. Mainly, the big difference is they're made from a file system that's 10 times smaller. And also, I constructed the read requests to be essentially as pathological as possible for the indexing, so that we were exploring as much of the index space as we can. And because the indexing behavior of the two different systems is slightly different, we do end up with some subtle differences between which of the old system and the new system are fastest, but that's okay. Until we get down to the really big requests when none of our systems are designed for retrieving 100,000 fields at once, and yeah, we hit the wall time. That's fine. But the real thing to note about this is the difference between the two columns in both cases. So on the left is when I've run these requests 10 times in a row, and everything's sitting nicely in the file system cache, and it runs very, very fast. And on the right is when I've made very sure that everything is completely clean, cold, running from a cold system that's had no requests going to it, and we have to get everything from at once. And we can see that the first accesses to the FDB5 are actually quite a lot slower, because we have to read the schema and multiple tables of contents, and it has an overhead for getting hold of these small files. It comes into its own when you have complex queries that hit a large part of the index space, and we can navigate the B trees in memory very, very fast. So there is a difference in the performance characteristics. But when we are looking at requests that are of the size that are used for the post-processing, we tend just to get pretty similar performance. And it tends to be limited by the rate that we can get data off the parallel file system, which, given that we have a whole load of post-processing processes in parallel, tends to be hardware limited. So then you ask the question, why have we done all this? If you've taken a parallel file system that you were hardware limited and replaced the system with something that's hardware limited, it seems a little pointless. And the answer is that the main motivation of all this work can be seen by the fact that we're in the scalability team where we're writing this. And as the data increases by successive factors of 4, and the number of fields we have to deal with increases, we're going to have some very interesting scalability problems. And we need to restructure the workflows for how we're working. So I've described a POSIX backend to this, but most of the work has gone into creating a unified front end and API that works in conjunction with the existing software stack, but is completely runtime configurable to do different things at the back. So at some point we're going to have a persistent memory backend. We're going to have a distributed backend so we can keep data hot, distributed across nodes in the supercomputer. And ultimately, we're interested, what are the new opportunities to adapt our workflows so that we don't have to write all our data to Lustre and read it back again 2 or 3 times down the data pipeline? Because that's where we're going to get a big win, is taking spinning disk out of this pipeline. The first thing that we're going to be looking at really, and is the project that I'm being funded through, is looking at the 3D crosspoint memory technologies that are going to be being released by Intel. And I'm nervous about saying too much because of non-disclosure agreements and so forth. So this slide just has stuff that you can pull off Wikipedia. But ultimately, we're going to have memory technologies with very high density, good durability, pretty good speed and latency, certainly much better than spinning disk, and at a vaguely sensible price. We don't really know how much we're going to be able to afford, how it's going to be plausibly distributed through supercomputers, but we know that this stuff is coming. So we're building our systems, and we have built a back end that will work on top of a node running this. So that's where we're going. But this is all a step along a pathway to a different future, which is a different perspective on all of our data. Ultimately, we can consider our data to be a very, very dense hypercube for our current resolution, it's about 48 terabytes of uncompressed data. When we go to higher resolutions, we can end up with nearly 200 terabytes or even over a petabyte of uncompressed data that is output by the model through a run. And this can be described by a lot of different parameters that are scientifically meaningful. This might be the level in the atmosphere, might be the location, might be the period in time. And people want to do different things with this data. And in particular, they want to slice it in different ways. And the view that we've always had in the past of two-dimensional fields around the atmosphere is going to become increasingly unhelpful. We want our clients to be able to slice across whatever axis is scientifically meaningful. And this is a very long-term goal that will only be made possible by being able to store the data in one location, because we can consider this to be a data-centric computing problem. We store the data hot in a node in a byte-addressable manner that we can slice as we like, and customers ship their functions for how the data is to be processed to us. We process that and return them a much smaller subset of data. That's what they actually want, rather than, if you want to do a processing on a time series of data for Lugano, you don't really want to have 1 day's worth of data for the last 15 days. So hourly data for the last 15 days in global fields shipped to you. That's not useful. And it's not useful for us to do the interpolation into a form that is a long sequence of subgrids either. It's much better for you to use semantic descriptions. You could use the Mars language or other forms, or even write them in Python or other languages, and write this in a scientifically meaningful way. Send it to us. We can work on the data. We have it. It's going to be in a hot node, and We think this is going to be where we're going to be going, and the FTP5 is a first step along the path of building the flexibility to have this access to our data in our forecast pipeline. The work I'm doing is currently part of the Next Gen IO project. It's a European Horizon 2020 project. We're doing three main things. We're considering the operational process, using persistent memory as large buffers. We're using persistent memory to store into an archive within the Mars ecosystem, direct transfers, and we're considering how we can use the data in new ways. Thank you very much.
Okay, thank you very much for the talk. We have time for questions. So maybe I will start with the questions that I had to the last speaker. So your paper has now been accepted in the ACM library. How would you extend your work? So we have three different journals. First one is ACM TOMS, Transaction of Mathematical Software. The other one is in physics, and the last one is in geophysics.
I don't think the physics and geophysics is going to be that applicable for this. What do you say the first was?
It's ACM TOMS, Transaction of Mathematical Software.
Yeah, I'm not sure. I fear my perspective is a little bit tied to what we're trying to do at the moment, but I think the big weakness that we've got here in this work is we've not done enough work at scale for how we think this stuff is going to work in a massively parallel sense in actual operational pipelines. So the thing that's coming up now in the background is we're starting to put some of this into the research workload, such that it's actually used in stuff that's meaningful, and I think at that point we'll have a better understanding of where stuff falls down, and that will allow us to more concretely address what the scalability issues are.
Okay, thank you.